Fundamental interactions, also known as fundamental forces, are the interactions in physical systems that do not appear to be reducible to more basic interactions. There are four conventionally accepted fundamental interactions: gravitational, electromagnetic, strong nuclear, and weak nuclear. Each one is understood as the dynamics of a field. The gravitational force is modeled as a continuous classical field. The other three are each modeled as discrete quantum fields, and exhibit a measurable unit or elementary particle. The two nuclear interactions produce strong forces at minuscule, subatomic distances. The strong nuclear interaction is responsible for the binding of atomic nuclei. The weak nuclear interaction also acts on the nucleus, mediating radioactive decay. Electromagnetism and gravity produce significant forces at macroscopic scales where the effects can be seen directly in everyday life. Electrical and magnetic fields tend to cancel each other out when large collections of objects are considered, so over the largest distances, gravity tends to be the dominant force. Theoretical physicists working beyond the Standard Model seek to quantize the gravitational field toward predictions that particle physicists can experimentally confirm, thus yielding acceptance to a theory of quantum gravity. Other theorists seek to unite the electro-weak and strong fields within a grand unified theory. While all four fundamental interactions are widely thought to align on a highly minuscule scale, particle accelerators cannot produce the massive energy levels required to experimentally probe at that Planck scale. Yet some theories, such as the string theory, seek both QG and GUT within one framework, unifying all four fundamental interactions along with mass generation within a theory of everything. General relativity. In his 1687 theory, Isaac Newton postulated space as an infinite and unalterable physical structure existing before, within, and around all objects while their states and relations unfold at a constant pace everywhere, thus absolute space and time. Inferring that all objects bearing mass approach at a constant rate, but collide by impact proportional to their masses, Newton inferred that matter exhibits an attractive force. His law of universal gravitation mathematically stated it to span the entire universe instantly, or, if not actually a force, to be instant interaction among all objects as conventionally interpreted. Newton's theory of motion modeled a central force without a communicating medium. Thus Newton's theory violated the first principle of mechanical philosophy, as stated by Descartes: no action at a distance. Conversely, during the 1820s, when explaining magnetism, Michael Faraday inferred a field filling space and transmitting that force. Faraday conjectured that ultimately, all forces unified into one. In the early 1870s, James Clerk Maxwell unified electricity and magnetism as effects of an electromagnetic field whose third consequence was light, traveling at constant speed in a vacuum. The electromagnetic fields theory contradicted predictions of Newton's theory of motion. Unless physical states of the luminiferous ether, presumed to fill all space whether within matter or in a vacuum and to manifest the electromagnetic field, aligned all phenomena and thereby held valid the Newtonian principle relativity or invariance. Disfavoring hypotheses at unobservables, Albert Einstein discarded the ether, and aligned electrodynamics with relativity by denying absolute space and time, and stating relative space and time. The two phenomena are altered in the vicinity of an object measured to be in motion, length contraction and time dilation for the object experienced to be in relative motion. Einstein's principle special relativity, published in 1905, special relativity was accepted as a theory too. It rendered Newton's theory of motion apparently untenable, especially since Newtonian physics postulated an object's mass to be constant. A consequence of special relativity is mass being a variant form of energy, condensed into an object. By the equivalence principle, published by Einstein in 1907, gravitation is indistinguishable from acceleration, perhaps two phenomena sharing a mechanism. That year, Hermann Minkowski modeled special relativity to a unification of space and time, 4D spacetime, stretching the three spatial dimensions onto the single dimension of time's arrow. Einstein arrived at the general theory of relativity in 1915. Einstein interpreted space as a substance, Einstein ether, whose physical properties receive motion from an object and transmit it to other objects while modulating events unfolding. Equivalent to energy, mass contracts space, which dilates time. Events unfold more slowly, establishing local tension. The object relieves it in the likeness of a free fall at light speed along the pathway of least resistance. A straight line's equivalent on the curved surface of 4D spacetime, a pathway termed world linear. Einstein abolished action at a distance by theorizing a gravitational field, 4D spacetime, that waves while transmitting motion across the universe at light speed. All objects always travel at light speed in 4D spacetime. At zero relative speed, an object is observed to travel none through space, but age most rapidly. That is, an object at relative rest in 3D space exhibits its constant energy to an observer by exhibiting top speed along 1D time flow. Conversely, at highest relative speed, an object traverses 3D space at light speed, yet is ageless. None of its constant energy available to internal motion is flow along 1D time, whereas Newtonian inertia is an idealized case of an object either keeping rest or holding constant velocity by its hypothetical existence in a universe otherwise devoid of matter. Einsteinian inertia is indistinguishable from an object experiencing no acceleration by existing in a gravitational field possibly full of matter, distributed uniformly. Conversely, even massless energy manifests gravitation, which is acceleration, on local objects by curving the surface of 4D spacetime. Physicists renounced belief that motion must be mediated by a force. Standard model. The electromagnetic, strong, and weak interactions associate with elementary particles, whose behaviors are modeled in quantum mechanics. For predictive success with QM's probabilistic outcomes, particle physics conventionally models QM events across a field set to special relativity. Altogether, relativistic quantum field theory. Force particles, called gauge bosons, force carriers or messenger particles of underlying fields, interact with matter particles, called fermions. Everyday matter is atoms, composed of three fermion types. Up quarks and down quarks constituting, as well as electrons orbiting, the atom's nucleus. Atoms interact, form molecules, and manifest further properties through electromagnetic interactions among their electrons absorbing and emitting photons. The electromagnetic field's force carrier, which if unimpeded traverse potentially infinite distance. Electromagnetism's QFT is quantum electrodynamics. The electromagnetic interaction was modeled with the weak interaction, whose force carriers are W and Z bosons, traversing the minuscule distance. In electroweak theory, electroweak interaction would operate at such high temperatures as soon after the presumed Big Bang, but, as the early universe cooled, split into electromagnetic and weak interactions. The strong interaction, whose force carrier is the gluon, traversing minuscule distance among quarks, is modeled in quantum chromodynamics, EWT, QCD, and the Higgs mechanism, whereby the Higgs field manifests Higgs bosons that interact with some quantum particles and thereby endow those particles with mass. Comprise particle physics standard model. Predictions are usually made using calculational approximation methods. Although such perturbation theory is inadequate to model some experimental observations, still, physicists widely accept the standard model as science's most experimentally confirmed theory. Beyond the Standard Model, some theorists work to unite the electroweak and strong interactions within a grand unified theory. Some attempts at guts hypothesize shadow particles, such that every known matter particle associates with an undiscovered force particle, and vice versa, altogether supersymmetry. Other theorists seek to quantize the gravitational field by the modeling behavior of its hypothetical force carrier, the graviton, and achieve quantum gravity. One approach to QG is loop quantum gravity. Still other theorists seek both QG and gut within one framework, reducing all four fundamental interactions to a theory of everything. The most prevalent aimito is string theory, although to model matter particles, it added SUSY to force particles, and so, strictly speaking, became superstring theory. Multiple, seemingly disparate superstring theories were unified on a backbone, M theory. Theories beyond the Standard Model remain highly speculative, lacking great experimental support. Overview of the fundamental interactions. In the conceptual model of fundamental interactions, matter consists of fermions, which carry properties called charges and spin plus or minus 1/2. They attract or repel each other by exchanging bosons. The interaction of any pair of fermions in perturbation theory can then be modeled thus. Two fermions go in interaction by boson exchange, two changed fermions go out. The exchange of bosons always carries energy and momentum between the fermions, thereby changing their speed and direction. The exchange may also transport a charge between the fermions, changing the charges of the fermions in the process. Since bosons carry one unit of angular momentum, the fermion's spin direction will flip from plus 1/2 to minus 1/2 during such an exchange. Because an interaction results in fermions attracting and repelling each other, an older term for interaction is force. According to the present understanding, there are four fundamental interactions or forces: gravitation, electromagnetism, the weak interaction, and the strong interaction. Their magnitude and behavior vary greatly, as described in the table below. Modern physics attempts to explain every observed physical phenomenon by these fundamental interactions. Moreover, reducing the number of different interaction types is seen as desirable. Two cases in point to the unification of electric and magnetic force into electromagnetism, the electromagnetic interaction, and the weak interaction into the electroweak interaction. See below. Both magnitude and range, as given in the table, are meaningful only within a rather complex theoretical framework. It should also be noted that the table below lists properties of a conceptual scheme that is still the subject of ongoing research. The modern quantum mechanical view of the fundamental forces other than gravity is that particles of matter do not directly interact with each other, but rather carry a charge, and exchange virtual particles, which are the interaction carriers or force mediators. For example, photons mediate the interaction of electric charges, and gluons mediate the interaction of color charges.